Today we're going to finish section 7.4. It's titled percent, and we actually looked last time at how we can use proportions with percents to find different quantities. There's one other component to this section that we're going to take a look at, and that component has to do with interest. And in particular, this one is still sort of connected back to, well, it's connected to both topics actually, but this idea of things increasing and decreasing and having interest to them. So this question asks, why is it possible to have an increase of 150% in price, but not a decrease of 150% in price?
Then it'd be a negative price.
Okay, yeah, so can we increase 150% in price? Sure. So we can always add, right? You can always add to a price. Right? So that's why I can increase. I can always add on to the price. I can make a 600% increase in price if I wanted to. We see it happen all the time in stores, right? They increase the price on things. That's normal. But if I decrease more than 100%, then I get a negative number.
I work at a retail store, and people get something off the 90% off rack, and they'll try to use their employee discount. And I'm just like, bro, you're not going to get 125% off chapstick.
So we'll actually talk a little bit about that because discounts work a little bit differently than quite just like adding things on, but sometimes people expect them to do that. They do. So let me finish writing this one, and then I'm going to actually talk about that real quick. And in particular, I can't have a negative price. That's true. And of course, your store is not going to send you away with the product and money, right? Yeah. So I guess I used to have an example in this set of questions that talked about your very same issue, Isabel, that you just mentioned. So every now and then you'll hear people talk about things where they think that they add discounts together in sort of an addition way. So if it's 90% off, like the example you gave, and they get what did you say their discount is? Like 25%? Their discount is 35%, that they think they should be able to add the 90 and the 35, and therefore they're going to get 125% discount. So that's not actually the way the percentage discounts work. What they would actually do is they would give them the 90% off, and there would be an amount. And then that amount they would get the 25% or 35% off of. So it ends up being a multiplication factor twice, not adding the two percentages and then multiplying. But that's a very common mistake that people get to a lot. We're going to encounter some other interesting common mistakes in your homework and things like that people think about percents and how they work. So I do have a little bit more in this section that we're going to do an application of, and in particular, it's interest. So interest is the amount of money that you pay or earn to borrow or lend money. So principal is the amount that the amount used to determine interest. So if you're borrowing money, it's the amount that you've borrowed. Or if you're putting money into an investment, it's the amount of money that you put into the investment. It works both ways. The interest rate is the percent used to determine interest. And the only one that we're going to talk about in this section that shows up is actually called simple interest. So simple interest has two equations. They're the same thing. One of them says A equal P plus PRT. The other one says A equal P times 1 plus RT. But notice if you distributed the P, it'd be the previous equation. Sometimes there's benefit into thinking of it in one way versus the other. It's also interesting that if you notice that if you distributed it and you ended up with this PRT at the end, that's the interest portion. So when you're actually finding simple interest, you take the principal let's talk about borrowing just so that I can do one or the other. The principal is the amount that you actually borrowed plus the interest, the price you pay for the luxury of having used somebody else's money. That's what interest is. So we're separating it into two ways. Here's principal, and here's the interest amount. So we're going to do a couple of examples having to do with interest. So a company is expanding its line to include more products. To do so, it borrows $320,000 at 13.5% annual simple interest for a period of 18 months. How much money will the company be charged? I want to flip back over here to make a couple of conditions that I just forgot to mention earlier. In all of what we're doing right here, your R is your interest rate, we just said, but it has to be as a decimal. So we have to turn it into its decimal form. And your time, T, is always in years. So if they give you a time, like this one does, in months, we have to figure out what that quantity amount of time is in years in order to use these equations. Because inherent in the way the equations are set up are those conditions. So the question asks us, how much interest will the company be charged? So the most direct equation that we can use is the very bottom equation because it just finds interest. So we'll use I equal PRT since that's the question that we're answering. So P, the principal, how much is that? That's my $320,000, good. Okay, so what is my interest rate? Just what does it say? 13.5%. So I need to take my 13.5% and I need to turn it into a decimal. And to turn a percent into a decimal, one of the ways we learned is just moving the decimal point 2 to the left. So that's our quickest option at this point. So this value R is actually 0.135. So it is a very common mistake for people to forget to move that decimal. It's also a very common mistake to forget that the time has to be in years. So here it said 18 months. What is that in years? Yeah, it's a year and a half, so I need 1.5. So as long as I get all my values, recorded properly in here, it's just a simple matter of using your calculator to find that. So grab a calculator. We're going to multiply out 320,000 times 0.135 times 1.5. And what do you get? $64,800. And of course it's in dollars, so we'll put our dollar sign along with it. That's the interest. Now another question we could be asked is how much will they owe back, right? Well, if we had been asked that, the most direct equation to find it would have been one of these two, these simple interest equations, right? But if we just sort of got to rolling and we forgot which one we were finding, whatever, at the end, and we realized, hey, wait a minute, how much they owe back is not $64,000, they borrowed $320,000. We could actually just add the $320,000 to this, and that would be the amount they would owe back. So you could also just work around it that way if you used, by accident, the wrong formula to start with. All right, this is another very interesting one, and I've actually been told that on the OGET in a different place that somebody was able to use this idea, this processing idea, in a very productive way. So that's one of the reasons why I have clung to having it in my notes, is because it was very helpful on the OGET at one point. Whether that question or that type of question is still in there, I'm not sure, but I know it's been reported back to me. So this says, because of a recession, the value of a new house depreciated 10% each year for 3 years. Okay, so it goes down in value 3 times. And then the economy begins to recover and the value of the house increases by 10% each year. So the question is, what happens overall? Did the 3 decreases get canceled out by the 3 increases? And if not, how did that play out, basically? Was there an overall increase or an overall decrease? So your gut may be telling you, well, sure, it went down 3 times 10%, it's going to up 3 times 10%, it's going to be a wash. So we're going to check that out. There is a caveat to this particular problem, and the caveat is that it doesn't tell us how much the house is, right? So if it doesn't tell you how much the house is, you just get to pick a value. So make it an easy one. So the value that I'm going to pick to make it an easy one is just going to be $100,000. because it's a reasonable number. That's a ballpark number for a house. And it's easy to work with. So we're going to pretend at the beginning, so this would be year 0, if you will, that the house is worth $100,000. Whoops, there we go. So if the price is decreasing every year by 10%, how much of its value is it retaining? 90%, right? If it's decreasing 10%, it's keeping 90% of its value. The reason I mention that is because we're going to do several calculations, and it's easier if I do the calculations with recognizing that I've got 90% each time. So I'm going to take my $100,000 and I'm going to multiply it by 0.9, and the value of the house after 1 year is going to be what? $90,000. And that should make sense, right? It went down $10,000 because 10,000 is 10% of 100,000. Sure. Now, year 2, it doesn't start out at 100,000 now. It starts out at 90,000. And my 90,000 will decrease by 10% again, but it means it retains 90% of its value. So what is 90,000 times 0.9? 81,000. So notice it did not go down $10,000 again, right? This time it only went down $9,000. And then the last year of decrease for year 3 is to take that 81,000 and decrease again by 10%, which means it increases, or it keeps rather, 90%. And what is 81,000 times 0.9? Good, 72,900. So this is the end of my decreasing value price, right? Like after this, the economy is going to recover, and we're going to go back up. So are we good so far? All right, so this is obviously a problem if they sell their house right now, correct? Right? This is why people talk about houses being long-term investments, is because decreases in economy do happen. I know, we got caught in one when we moved back to Oklahoma. It was significant. So after that, our houses are going to go back up in value. So I'm going to take that same value, that $72,900 that it's worth at the end of 3 years. But now it's going to go up 10% in value. Okay? So what does up 10% in value look like? Well, I need to be multiplying by something bigger than 100%. I would be having 110%. So what is 110% as a decimal? Yeah, it's 1.1. So 90% was 0.9. 110% is 1.1. Whoa. There we go. So I'm going to multiply 72,900 by 1.1. And what am I going to get? Yep, 80,190. And we're going to do this for year 5. So my 80,190 multiplied by 1.1. What number did you guys get?
82.
88,209. And the last year takes the 88,209 times my 1.1. And what do I get? Yeah, I'm just going to round to the nearest whole dollar amount. So we're going to, because that's reasonable for talking about the price of a house, $97,030. Okay, so it started out as 100,000. It ended up as 97,000. The question asks us, did the house increase or decrease after the 6 years? It decreased. Now, it's a heck of a lot better than at the end of year 3, right? But overall, I still saw a decrease in value. Now, it's a little tricky because I can't really say it decreased a specific dollar amount because I made up the $100,000, right? That was arbitrary. It's just a nice number. So if we're actually looking to see how much it really decreased, we would have to do something by looking at the percentage that it decreased so that we're eliminating the fact that we chose an arbitrary $100,000 house. So this question, when it talks about it, says they wanted to find out the percent that it increased or decreased over time. Now we can find out from our arbitrary numbers the dollar amount very easily. How could I find out the dollar amount given these conditions that this particular house would have decreased? Yeah. You take your original value, and I'll do it that way, that's fine. And I take off the value I ended up with, which was $97,030. Okay. And then I have to eliminate the fact that I made this arbitrary $100,000 choice. And the way that I do that is I divide by the $100,000 that I made as my choice. So what this does is it eliminates the fact that I made an arbitrary choice. So let's say I did this one, I did $100,000, but when Mel did hers, she chose to do a $200,000 house. So her numbers are going to look different. She's going to have a $200,000 minus a different number over here, right? And she's going to be dividing by $200,000. And when we both do our calculations, our percentages are going to come out the same because we've eliminated that arbitrariness by dividing by it. And then we're going to multiply it by 100 to get it back into a percent. So I take 100,000, I subtract my 97,030, and I divide by 100,000 and then divide by 100. So 100,000 minus 9730. So on top I now have, 2970 dividing by 100,000. And then times 100%. And I have a 2.97% decrease. Right? It's decreased because we saw the number went down. So overall, about a 3% decrease in the value of the house. Way better than the 10% 3 times, but it's still a decrease. So starting in April of 2020, I actually started keeping track of all of the COVID data in Oklahoma every week until right before Delta hit. And I didn't know Delta was going to hit, or I would have kept going because it would have been very interesting to have that data too, and I don't have it. But I kept data for a long time. And the reason I did keep data is because I wanted to be able to use it for real life problems. So I wanted to create for you a real life problem, and that's the one that you're about to see next. So as of August 1st, 2020, the total number of positive cases, and this is all state of Oklahoma data, total number of positive cases of COVID-19 in the state of Oklahoma stood at 37,731. The population of the state of Oklahoma on July 1st, 2020, which I realize is not August 1st, but I couldn't find it for August 1st. So we're going to go with a little bit of error of accuracy here, okay? Was 3,956,971. So the first question that we're going to be using here to talk about percentages is going to be to find what the percentages of Oklahomans that had contracted COVID-19 on that date. Okay, so what do? Well, we're doing it just like we had done before, much like this last problem over here. We're looking at how many had contracted it, right, who'd actually obtained it. That's that 37,000 number, 731. And we're going to divide by the number of Oklahomans, which is really close to 3,956,971. And then I multiply by 100% to get it into a percentage. So you can grab your calculator. If you multiply by 100, it will be 0.95, we'll use 2 decimals for now, percent. Now percentages are really tricky. They're almost like dollar amounts. They throw people for a loop. A lot of people will look at this and say that looks like 95%, and it is definitely not 95%. There is a decimal there and it has a meaning. This number is less than the number 1, right? So you want to be really careful when you're looking at the values that you interpret them with the right context. This is less than 1%. And that wasn't how many had it at that time. That was how many had accumulatively had it since they started tracking. Well, since I started tracking anyway, which was in April 1st. So from April 1st all the way to August 1st, less than 1% had the virus. So since we're talking about school-age kids, because you guys are going into the teaching field, I wanted to do something related to children. So 10.92%, almost 11%, 10.92% of the positive COVID-19 cases were in kids. Kids ages 0 to 17. So in particular, mostly school-aged kids. That's not everybody, right? I realize that the first 5 years are probably not included, but we got something pretty close. So the first question it asks is, how many kids does this reflect? So this is 10.92% of the cases that were positive, which was the 37,000 cases. Okay? So almost 11% of those 37,000 cases. So we've got our 10%, which is 0.1092, 10% of my 37,000. Where was it? 731 cases. So I've got my percentage. You could also set this up like we did before, where you put the 10.92 over 100, and it equals my X value that I'm looking for over my 37,730. Was it 731? Yeah. And then cross multiply. You'll have the same thing. So if I take 0.1092 times 37,731, and we got to round to a whole number because these are kids we're talking about. No halves of children. That's not a good plan. How many kids does this represent? Yeah, 4,120 kids. Okay, so from April to August, 4,000 kids in the state of Oklahoma got COVID, give or take, right? So again, my data isn't perfect because it goes to July 1st, not August 1st, but there were 981,328 kids in Oklahoma on July 1st. That's the kid data, whereas our population data was the 3 million, okay? So our kid data is the 981,000. What percentage of children in Oklahoma had tested positive? Right, so the percentage of people in Oklahoma was just almost 1%. What's the percentage of children in Oklahoma? So we have our 4,120 children out of our 981,328 total children. And again, this would go clear down to age 0, so not even all of those that would be school age. And then multiply by 100. And again, you could set this up with a proportion if you'd like. You would have the same value right here. Let me set it up as a proportion just so you can see it. And you would set it up equal to x over 100 and multiply if you want to set it up that way. Either way you set it up, multiply it out. We'll go with 2 decimals. What do you get this time? 0.42. So roughly half of the population in general, right? Roughly half. So 0.42% of all the children. So that would look an awful lot like 4 out of every 1,000 kids coming into the building. That's what that means. 4 out of every 1,000 would have at some point contracted COVID at that point. I even have that written down. 4 out of 100,000. Because if you took 4 divided by 100,000, you'd get about 0.4%. All right, we have 4 group work problems, so we're going to pause and you guys can take a look at starting those.